Okay, hi science bowlers. Let's talk some electricity stuff. All right. Current. Current is the rate of charge passing point. So charge is in coulombs, and time, of course, is in second. And so that's the definition of an amp. So an ampere is a unit of current. So I've even seen problems where it asks how many coulombs of charge passed by a certain point in a given amount of time given a current, right? So this is clear how to use that. Current often goes through resistors, and that when a current goes across a resistor, that means there's a potential drop across that resistor, right? So there's the current, and that voltage drop across the resistor is equal to the current through that resistor times the resistance. This is Ohm's law, and not all objects are ohmic, which means they don't follow this equation. Light bulbs are ohmic at low temperatures, but R increases with temperature for most things. And so I can't think of a counterexample right now. And so that, if it gets too hot, then it's not going to be ohmic anymore, right? Because then you get this nice V versus I, and then your slope is R. So that's nice. Series. That means that each resistor gets the same current through it, and the equivalent resistance is R1 plus R2. If resistors are in parallel, then the current splits. So you get I1 and I2, but the voltage across them are the same. And then you get this fun inverse stuff to give you the equivalent resistance. Equivalent resistance is important because, here, I'll just draw it up here. If you have a battery and you have a variety of resistors, by the way, this E, that's EMF. It's another word for voltage of a battery. EMF stands for electromotive force. Historically, they didn't understand what they were looking at, and they were like, oh, look, charges are moving, there must be a force on them. And they called that the electromotive force. It wasn't until later that they realized that that was the same thing as a potential difference. So this historically, EMF is still used, but it's not a force. It's potential. So anyway, if you have a series of resistors, I don't mean like series as in series, I mean like a chunk of resistors, what the battery does is it looks out there, it does all this math, and it says, how much resistance is there really, right? And it finds out the equivalent resistance of the circuit, and then it pumps out a current, right? Here's your V equals IR. It pumps out a current equivalent to this, the EMF of the battery divided by the equivalent resistance. All right, groovy. Very often we talk about power in circuits. So what is power in general? Power in general is an energy per time. So units, you've got a joule per second, and that is called a watt. Right? That's a watt. And so, like, I've seen questions asking about how many joules are in a watt hour, right? So a joule is a watt second. So I believe in you. I know you can do it. I know you know how to do that kind of problem. But that's just a reminder of what you see. Back to seeing power in, while we're talking about power, and I have you here. So power is, right, an energy per time. It's also a force times a velocity. If you have something with a constant force at a constant velocity and it asks about the power used to get that done, it's F times V. It's a, useful little thing. I don't know if it actually shows up in Science Bowl, but that is useful. Okay, so when we're talking about circuits, we're often talking about the power dissipated in a resistor. That's a very common thing for them to ask about. And in general, power in a circuit is the current times the voltage across it. For a resistor, we can substitute in V equals IR and we get I squared R, which is really, really common. I've seen a bunch of problems in Science Bowl where you get power as I squared R. If you have voltage instead of current, it would be V squared over R, which is where we sub in I is V over R. So if you want to know about the energy, the total energy dissipated in a certain amount of time, right? Because power is energy over time, energy is power times time. And so I squared RT is something that often happens. I squared R, by the way, just because every now and then they like to throw random words at you. This is often called Joule heating, because what happens is, the current goes through the resistor and it heats up, right? That's this energy, it goes into heat. And so Joule heating, this is why a light bulb feels hot to the touch, right? Cool. I think that's all I wanted to say about that. For this video, let me do a couple other random things. There is a word, triboelectric charging. And this is, just that charging by friction. You rub a balloon on your head. You rub a glass rod with silk. Let's talk about that one, actually. A glass rod with like a silk cloth. There's something called the triboelectric series, which tells you which materials, like to give up their electrons and which materials like to take in their electrons. That is not something that I've ever committed to memory, but you science bowlers, occasionally might like to do that. And actually, I found a question where it asked, when glass and silk are rubbed together, like what happens? So all I knew was the electrons go one way or the other. I don't know which way, but apparently the electrons go to silk, which then, of course, means that you end up with a positive glass rod and a negative silk. But honestly, triboelectric charging, this is just an application of conservation of charge. Okay? Just saying, the number of electrons that the glass loses is how much the silk gains. Okay. Well, while we're just riffing on conservation of charge, Kirchhoff's, so this is Kirchhoff's law. Everybody says Kirchhoff, but I can't not see that as a German churchyard, except maybe there's no other F. Anyway, sorry about that. Got a little distracted. The junction rule, which says in a circuit, if you've got a current coming in, that equals the current coming out, and that's because of conservation of charge. Any charge that comes in here either has to go there or there. So, I in equals I out is the junction rule in Kirchhoff's laws. I1 equals I2 plus I3. Conservation of energy is the loop rule. And I've seen this mentioned in Science Bowl stuff, otherwise I wouldn't have mentioned it. Loop rule is you have basically like a multi-loop circuit. That was a resistor. And it says if you go around a loop, that the sum of all the potential differences is 0. And, you know, that'll be a lot more clear when you actually take my class. But for right now, this is conservation of charges, junction rule, conservation of energies, loop rule. Groovy. Here, that's a good place to stop right now.